talk has already mentioned problems about how you deal with model ensembles. I won't provide a complete answer to that, but I will provide at least some direction and what I think is kind of known in more general statistical literature about this. I apologize, I'm going to show you some matrices before lunch on a Monday, which is probably unkind. But I have skipped most of the theory, so it shouldn't be too bad. And I am going to try and introduce data assimilation on the way, so let's see if we can do all that in 20 minutes. First, a couple of acknowledgements and references. In particular, I think a really interesting book from Edwin James, who described a lot of the basic theory I'm going to use. And I think, in fact, I've only realized recently that what I'm talking about is kind of an application of one of the chapters in his book. So I, as usual, reinvented the wheel, and I just hope it's round. A usual comment when I'm talking is if I appear to be talking about a completely different slide, it's because I can't see what you're seeing, and my notes and myself got out of line. So please tell me if that happens, and I'll try and get things organized. Here's an outline. I'm going to talk about data assimilation for research, the differences between using DA for research and using it for standard prediction, a little bit of theory, and really the rest is just an example from an old intercomparison that we ran in the atmosphere and how I think it can be improved with some of these methods. So what does data assimilation try and do? The data assimilation, you can say in words, it looks for a trajectory of an evolution of a system in time that is consistent with some model dynamics. The model dynamics can be anything, it's just a way of writing down the way we think we understand the system behaves, and also consistent with some observations. Now, consistency is used as a word here, but it in fact has a range of statistical definitions. We mean it in some statistical sense. And usually we're aimed at improving either parameters of the model, so some constants we don't know in the model, or often, as in, say, weather prediction, the initial state. Now, all of this assumes that the model is actually capable of doing this. We can almost always get an answer. It's a difficult problem to know whether the answer is worth having. And the good thing is we can usually diagnose whether we've failed. This title is not true. We can't quite do data assimilation in one picture, but we can do it in two. And this is taken from a paper that I wrote actually coming out of the Terabyte Symposium, the first Terabyte Symposium in Hamburg. So this is how data assimilation works. We have a very simple model here, one unknown, one observation, and a very simple model. The very simple model says that the observation is equal to the unknown. And for all of these, we have we describe our knowledge about the model, the observation, and the unknown by probability distributions. Here they're simple, flat probability distributions. So the unknown is on the x-axis, the observation is on the y-axis. The light blue rectangle is our prior knowledge for our unknown. It means it can range between minus 0.2 and 0.2. We have an observation that goes between 0.8 and 1.2. That's the light red. The green is the model. Again, it's not a very good model. We're not very confident. It's a big fat rectangle that describes what kind of spread we can expect for a given value of the unknown. And then we find the solution. We find the solution graphically just by looking at the overlap between these probability distributions. Quantitatively, we actually multiply the PDFs. On this graph, you see the same diagram again on the left, and on the right, we see the solution. And the solution is got by saying, okay, what probability can we assign to various values of the unknown given the observations of the model that we have? And it says there's a little triangle there. We kind of project our solution onto the x-axis, and we get a solution which says that high values, values near 0.2, are more probable than low values because they overlap with more of the model and the observations. That's all fine. Now, we have a second version of the modeler, and she's a bit braver than the first version. So she says, no, in fact, we're more confident of our model, so we should use a narrower rectangle. And we do exactly the same thing. We have, again, the rectangle, but the rectangle is a little narrower here, representing greater confidence, and there's no overlap. So what that says is that it doesn't work. We can't find a joint state of the observations and the unknown that is consistent with the model dynamics. And what we normally do with this is say, oh well, she was a bit overconfident. We expand the rectangle, the model rectangle or the observations or whatever back to the original and get an overlap, and we're happy with the answer. And there are algorithms which are becoming increasingly used in terrestrial modelling. They've been used in the atmosphere for a while for diagnosing how much we should decrease our confidence in order to actually get an answer. But what modelers really do is something different. What modelers really do when they see no overlap is say, the model must be wrong. So now we have, again, two cases here. We have our old favourite on the left with, again, the large rectangle for the model. And on the right, we see another modeler came along and said, maybe in fact the relationship between the observation and the unknown should be different. It's, instead of being equal, one is equal to twice the value of the other. And what's more, I'm pretty confident about that answer. And so what you see is now two solutions, one of which is the triangle we've been seeing all along, the second of which is a smaller triangle, but it also corresponds with a more confident model. So how do you know which of these two is actually better? The second modeler was being more demanding and still managed to produce an overlap, just not as big an overlap as the first model. So how do you know which is better? And that's a different kind of data assimilation. It's, if you like, a discrete problem. Normally we ask, what's the probability of our unknowns? Can we get improved knowledge of the unknown parts of the system? We can ask a different question, which is, which of these two models is more likely? And it turns out that we can, in fact, do a rigorous, hopefully, statistical analysis of that problem and come up with an answer that gives us some confidence in which model is better. Now, a tiny bit of theory. Here's where the matrices come in. Sorry about this. All this really is the equation for a Gaussian probability. We'll need it a bit later. And the main thing that you see is there's a matrix determinant on the left. For those of you lucky enough not to know what matrix determinants are, it's just a volume of how big a matrix is. And then there's an exponential of something which is the difference between a value and its central estimate or mean divided by the same matrix, effectively. And that's the normal form for the Gaussian distribution. Now, we normally assume Gaussian probabilities in most of our cases. In fact, the theory I'm about to develop here doesn't need that. Now let's assume that instead of just having two models, as we had a couple of slides ago, we've got a whole bunch, m of them. They can be quite different models. They can have different numbers of parameters, have different confidence in those parameters, and whatever. And we're going to ask, we've got an ensemble of these, we're going to ask what's the most probable model. Now, if you remember earlier, I said that in order to find the solution, we multiply a bunch of parameters, a bunch of probability distributions together. And here we do just the same thing. We multiply the probabilities together for all of the different models. And then we go away for a few days and bang our head on the wall in order to try and get the algebra to come out, which hopefully it does. And we come up with a very disturbingly complicated looking answer. This looks horrible, but what you see is basically the same thing. It's a matrix determinant out the front, and you have a vector inside, and it's weighted by the same matrix that you see out the front. So you can guess that what you see here is another Gaussian probability distribution. The matrix is equal to the sensitivity of the unknowns, of the observations with respect to the unknowns, multiplied effectively by our uncertainty in the prior parameters and with the uncertainty in the observations added. And the vector that we see in the exponential is equal to the observations minus our first guess of what those observations should have been. And we also have another equation that says we're going to have to choose one model, so the probability of each of the models has to add up to 1. The sum of the probabilities, has to add up to 1. So this looks temptingly close to a recipe for calculating the probability of a given model, and we'll come back to that. Because I'm cruel, I'm going to keep showing this equation at the top of each slide here so that you don't have to try and remember what it is. The theory I skipped says that that equation tells you that the probability of a given model being true is equal to the probability of predicting the observations, given the uncertainty in the parameters and given the uncertainty in the measurements. And that's almost what you'd expect intuitively, but it turns out that it comes out to be true. And so you can calculate how likely your given models are by calculating the mismatch with the observations, but weighting that mismatch by the expectation, by how bad you would expect that mismatch to be. That's not normally what we do. What we normally do is calculate the mismatch with the observations, and for two different models, where one might be more complicated than the other, we don't know how to weight that mismatch. And so what we've given here is some way of doing that. A few notes. What you saw in the exponent is half the value of the best cost function you can have. How close do we get to the observations? And the whole quantity that we see is actually very close to the same quantity that we use to predict, to estimate the confidence that we should have in the model. So there are a series of papers around that say, well, if the mismatch is pretty bad, how much do we have to relax our confidence in the model or the observations in order to bring things back to being nicely behaved? And they actually work on the same expression that we see here. And the other thing to know is that the log of this beast, or some multiplier thereof, is very close to something that's around in statistics called the Bayesian information criterion. It's not quite the same thing, but it's close enough that I'll use that title from here on. So where there are techniques that are used in things like linear regression for judging models, and where we've developed here a criterion which is a bit similar, but a little bit more general. Some rules of thumb for judging models. If you're a model developer and you've just come along and you said, my model's a bit simple, I'll complicate it a bit more and see if I can match more of the processes, and you can generate this number. And how do you know if you've actually made much of a difference? Well, in general, particularly with a lot of observations, you want this information criterion to improve quite a bit before you can say this model is better than that model. There are pretty strong random fluctuations that you might get, but there are pretty well tested kind of rules of thumb. If you see an improvement of more than 6, then you can be pretty sure you've made a substantial difference. Now, an example. This is an example from the atmosphere. Apologies in a terrestrial conference, but as far as I know, this hasn't been done for an atmospheric case yet. It's a paper that originally came out 10 years ago from Kevin Gurney in Nature, where we tried to estimate the carbon fluxes from large regions of the globe, kind of half a continent and an ocean basin, which we thought was consistent with the data we had at the time. There was a great deal of uncertainty over these estimates, some big arguments that started in the late 90s about how big a sink North America was. We simply ran inversions with a whole bunch of different models, 17 of them in this case, kept everything else about the inversion constant. The data that we used, the prior estimates that we used, etc., we just changed the model. Perfect fit for the problem I just described. And we're going to show the case of the annual mean. 26 regions we estimated for, as I said, we had 17 models to contribute. What I'm going to try and do here is estimate how good those models actually are. This was an immediate criticism of the paper. We published answers, and people said, that's fine, but you're assuming all the models are equally good. Should you? And the answer is no, we shouldn't. We'll see in a minute. Here's the answer. This diagram usually takes 10 minutes to explain on its own. I'm going to give, there's only one thing about it that really matters here. What we see is what's called a box and whisker plot for the 26 regions. The boxes show the spread that we expect in the prior. So it's the horizontal bar says this is what our prior estimate was. The box shows you how uncertain we think that estimate was. And the bars, the vertical bars, show the answer. And there's two things I want to comment on here. The distance between the circles on those bars are an estimate of the uncertainty that we get because we don't have enough data, and the data doesn't constrain the observations well enough. That's something that's estimated, of course, by any data assimilation. You get a probability distribution, so that has an uncertainty. The length of the bar says how much uncertainty do we get because we had 17 different models. And you can see it's pretty big. In a lot of cases, the uncertainty due to the difference in models is as large or larger than the uncertainty due to the fact that we don't have enough data. And can we do something about that? When we published the paper, we published the mean, I think, is shown by the X, and that mean is calculated with all the models being equal. So I went through and calculated that number, that horrible equation, for each of these 17 different models, and here we show a range of them. I'm actually showing the log value, the information criterion. You see a tremendous range. In general, low is good. It means that the cost function is small and the confidence is high. So we see values ranging over, what is it? Values of about 50. And remember that the probability of these things is the exponent of that. So it's a huge spread in the performance of these models in matching these observations. So it's very strong discrimination. I actually, when I did this first, I thought with the uncertainty we have in the parameters, we won't be able to distinguish between the models at all. And we turn out to have the opposite problem. The distinction is too good. You have to be a little bit careful here because you're punishing models unduly from the fact that they make the same error several times. So I won't show it to you too much, but you have to do a little bit of work on dealing with correlated errors in the answers. It's another problem to deal with. A few things that you'll have to take on trust. The good models, the models with the low values of this information criterion, tend to cluster together. The outliers also tend to be outliers in how they predict the data. Now that didn't have to happen. It turns out that the data not only constrains what the parameters were, it also gives a good constraint on which particular model you should use, and the answers from those models are more similar. You look at just the cost function, how well did you do in hitting the obs without worrying about how well you expected to be able to do. In this case, it's a pretty good predictor. It isn't a good predictor when the models have very different complexity. These models are identical in their complexity. You can do this with models that are vastly different in a terrestrial model, for example. What can you do with this now? Well, the first thing you can do is test the model performance. It turns out, just for historical reasons, that the two models there that produced the worst match to the observations are no longer used. Now, that's probably because they were looking at their ability to hit the models and they didn't feel they could defend them when they came to do the next version, so they've changed a lot. That relationship between the cost function and the information criterion won't work when the models have different complexity. You can produce a probability-weighted ensemble. I actually tried to plot one here, but I couldn't reproduce that fancy box and whisker graph, so I couldn't do it. The amazing thing is that the model spread that you get from this calculation actually halves roughly when you consider how well the models actually do. So again, there was no rule that said that had to happen. So I think when calculating weighted ensembles, when calculating model ensembles, there is a method for taking into account how well the models actually work, and it will generally reduce the ensemble spread. Finally, a recipe for people who are actually doing this. The most important thing to know, this is particularly for terrestrial models, is the sensitivity of the things you're simulating to the unknowns in your model is an incredibly useful quantity. And it's fairly easy to calculate. You can usually calculate it just by varying the parameters a bit. You can do it with fancy software as well, but it's not a particularly hard thing to do. I kind of now recommend to students and so on I'm working with that when they have a new model, that's the first thing they do. That they understand the sensitivity of the outputs with respect to the inputs. Now we have a direct use for it. This is actually quite hard in the atmosphere, but it's fairly easy for terrestrial models that have many fewer parameters than there are flux components. You can calculate this probability, this BIC, and if anyone is still awake and curious enough, I provide some software to do that. It's actually easier than doing it in version. So you have now a chance of knowing whether the model improvement you've made makes a difference that's greater than you'd expect by luck. I'm going to finish with some advertising. There's a school, an autumn school coming up on the assimilation and by geochemical modelling being run at the Institute of Theoretical Physics in Terrestrial in Italy in late September. And the idea is to think about assimilation diagnostics like this, the kind of cutting edge, hopefully, of what people are actually doing in assimilation. And we're going to use a range of simple enough models that we think we can deal with them computationally easily hands-on, and so that the school is going to be a mixture of lectures on assimilation in general and kind of new techniques in particular, and then a series of hands-on exercises. And that's going on from September 20 to 27. There's a URL there that you'll see as we put the talk up. And I'm certainly going to be there teaching on some of this kind of stuff, and I'd recommend that. Finally, the conclusions. I'm amazed if I'm still in sync with my slides. It is possible to generalize data assimilation to actually choose among models. So the problem of being faced with a model ensemble which you know is going to produce a more reliable estimate, but not knowing what to do with it, I think is addressable. I'd be surprised if theory will come up with here as the final answer to this, but it's a step. There are some relatively simple and general diagnostics you can make of model performance. They're actually easier to use than data assimilation itself. And it looks from the examples I've seen so far that they'd be pretty easy to apply to things like terrestrial model and comparisons, and that they can significantly reduce the uncertainty you get due to an ensemble spread. That is, that the data can tell us not only about the dynamics of a given model, but compare the dynamics of various models quite successfully. I'll stop there.
There are some questions.